to the 9th lesson of this series of videos on mathematics of quantum mechanics. And in today's video, we are going to learn that why we use matrix algebra and all those matrix calculation in quantum mechanics. Before going into matrix algebra, it is very important to understand that the reason quantum mechanics uses matrix algebra. We are going to look a little bit more on Hilbert space, what are the different properties of Hilbert space, and the bra and the ket and the complex conjugate, how do they work. We are also going to look into something very important which is called Heisenberg's metric mechanics and some more properties, fundamental concepts and more details on this video of quantum mechanics. My name is Shaunak and you're watching this video on my channel Physics for Students. A warm welcome to the 9th lesson on mathematics of quantum mechanics. Just to note that this video pertains and contains more on the why part, because doing any mathematics on quantum mechanics, it is important for all of us to know the reason why we are doing that. So let us quickly look into the topics we are covering. So first we would do a quick recap for those who have missed the video, although I have given the earlier video in the I button, the entire playlist, but still a quick recap is good on Euclidean space, vector space, complex space and Hilbert space. We are also going to look what is a Hilbert space, because the entire quantum mechanics revolves around Hilbert space. What are the properties, the bra vectors, the ket vectors, and how do they come in terms of complex conjugate, why we need matrix algebra in quantum mechanics, the concept of qubit, Heisenberg's metric mechanics, and some of the matrices fundamentals. So these are the topics that we are going to cover. Don't worry if you have missed the earlier video, because I'm going to give a quick recap on all those topics. So first let us go for a quick recap. Now we have learned earlier that what is a Euclidean space. All our school level mathematics and geometry consists of Euclidean space. So we can say it is a fundamental space of geometry. It represents the physical space that we look around, all the objects, lines, polyhedrons, polygons, etc. And you can call that in mathematics it's an abstraction of the physical space that we see. From there we further get into vector space. So what are the vector space? Vector space is where the vectors reside. You can say it can be a generalization of Euclidean space is in a much more broader fashion, and it is a space where the vectors can be added, multiplied, and further manipulations can be done. From vector space we also learned earlier that what is a complex space, and in my earlier videos I have dealt much more details into complex plane and complex space. So it deals with something which are called complex numbers, obviously, and quantum mechanics completely depends and resides on complex space. We also have seen what is called a Hilbert space. Now Hilbert space is basically a quantum system where every possible state of the system can be represented on a Hilbert space, and it is basically an infinite dimensional Hilbert space. It is denoted by this curly h, and here you see that from the finite dimensional Euclidean space we now move into infinite dimensional space, and that is what actually Hilbert space is all about. Okay, so in the earlier video, what we ended, you have seen that these are the possible states that we call, and this is, we can imagine to be a Hilbert space, this blue one. And Hilbert space is a space populated with all possible states that a quantum system can found upon. And what is a quantum system? Here is the definition. This is a mathematical entity that provides probability distribution for the outcomes of each possible measurement. That means this psi1, this bra and ket, don't worry, we are coming to that. These are all possible states that the quantum system will be. And quantum system itself means it's a mathematical entity that gives us the probability distribution possibly where the electron would be. So this is a quick definition, and we learned that we need to understand about these properties: superposition, dimensionality, normalization, basis, and completeness. And now we are going to look into that, but before that I would just like to tell you that Hilbert spaces allow generalizing methods of linear algebra and calculus from finite dimensional Euclidean vector spaces to spaces which are infinite dimensional. So Hilbert spaces arise naturally and frequently in mathematics and physics, typically as function spaces. Okay, so let us first understand that what are basically the properties of Hilbert space. Right. Now, first of all, let us understand that the state of a physical system in quantum mechanics is represented by a vector belonging to a complex vector space. If you want, you can go back to my further videos in the playlist to understand more about complex vector space, but I have just given you somewhere where the complex numbers reside, that is called a complex vector space. This vector space is known as the state space of the system. So this is a vector space and this is called the state space of the system. Okay, a physical state system is denoted by a symbol and this is called the ket, right? And this has been coined by the famous English mathematician Paul Adrian Maurice Dirac, and that is why it is called as a Dirac notation. So the notation actually is very prominent in the description of quantum mechanics. And also note that ket notation is also called a state vector or a ket vector or state. Why? Because it represents physical state of a quantum system. Just now we have read it. So now what we see is that the set of all possible state vectors, because you see from physical state of quantum system we denote it by a ket. Ket is known because it represents a quantum system state vector, ket vector and state. Now the set of all possible state vectors describing a given physical system forms a complex vector space, which is this one, that is the curly H, which is the Hilbert space of the system. You can think of the Hilbert space as a space of all possible states that a quantum system can be found. I've just shown that. And Hilbert space actually inherits some of the properties of the normal vector spaces. So here is the Hilbert space. You see these are the possible vectors and we have just shown that. Right. So what are the properties that it inherits? First of all is something which is called superposition. Now what I'm trying to tell you is that a linear combination or superposition of two or more state vectors, this one psi1 psi2 dot 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 and it goes up to n, is also a state of the quantum system, obviously, because this is a linear combination. And therefore a linear combination of this can be formed something like this, where these C1, C2 and C3 are complex numbers. You can see that I have just done a kind of a summation, nothing more than that. This is one of the property which is called superposition, the first property of Hilbert space. Okay, the second one is called normalization. Now what do I mean by normalization? In general, for a physical state of the system is given by this vector psi, right? Now this same physical state can be represented by a vector. This is the physical state of the system, can be represented as C phi, which has got a bra and a ket, where C is basically a non-zero complex number. It can be anything, non-zero complex number. Now the reason is that for the overall normalization of the state vector doesn't change. So you can see it can also be represented by the vector. Now this is important. The overall normalization of the state vector does not change the physics of the system, or we can say in other words, it doesn't modify any kind of information that contain the state vector. As we will see in the further mechanics, that it is advantageous to work with normalized vector, that is whose length is 1, because it gives the possible outcome of an electron or a subatomic particle. So this is called normalization. So the overall normalization of the state vector doesn't change. Next, what is called is a completeness. Now if these are the state vectors, right, it is said to be complete if every state of the quantum system can be represented by a linear combination of them. Now when I say linear combination, it automatically means that the span of the Hilbert system, this one, right, so this is the case, and linear combination actually means this one. So in such case it is possible to express this state vector, as you see, as a span of the Hilbert space, and these are the I have just kind of summarized this with a sigma notation, and these are Ci. This one is a choice of the coefficients. Okay, next comes what is called a basis, and you all know that if you get a set of vectors, something like this is said to be form a basis for the state space of the set of vectors is complete, and if in addition they are linearly independent. Now remember, when I say linearly independent, what I'm trying to say is that we cannot express it on a given basis of a vector as a linear combination of the rest of the basis vectors. So linear independence can also be expressed as one of the requirement. So we can say it something like this, right? Where Ci equals to 0 for all the I. So this is another important. The set of vectors is said to form the basis when it is linearly independent. Okay. So what is the next property? Now this is something important. This is called dimensionality. Now what is that? The minimum number of vectors required to form a complete set of basis states is known as dimensionality of the state space. Now remember that in quantum mechanics we will encounter a lot of Hilbert spaces which has different type of dimensionality. Don't worry, this would require a separate kind of a video, but just to tell you that, for example, Hilbert space of a spin half particle, it lives in dimension 2. Free particles live in infinite vector space. We have something which we will learn which is called a qubit, which is called a two-dimensional vector space. Then it goes for dimension 4, which is called q-quart. Then goes for dimension 3, which is called quitrate. And anything which is dimension more than 2 in general, this is what is called qubit, right? So this is how it happens. Okay, so now that we have understood what are the different, I would say, properties of Hilbert spaces, now it is the time that we move ahead to understand what are the bra vectors, because we need to expand the Dirac notation. Now see, we have learned it, this is the ket, and this is actually the bra, right? So we are extending the Dirac notation. So we need to introduce this quantity, and this is known as the bra vector. So bra plus ket total makes the bracket, and this is how the bra vector looks like. It will have an angular bracket followed by a side, followed by a horizontal bar, which represents actually this one. It actually represents the complex conjugates of the corresponding ket vector. So I hope you can guess from there that every bra vector will have a corresponding ket vector. Now you see this, if a ket vector is given as this one, the bra vector will be this. And the most important thing that you need to note is that you see this changes. So the vertical changes to angular bracket and the vertical shifts one. Second thing, we have done a complex conjugate, so we have put a star on that. And most importantly, this one is also written in a different way. So these are the changes. So each complex conjugate will have a corresponding ket vector. So now you see that this one, the bra vectors are elements of the vector space. This one, which is H star, and this is actually called the dual space of each and every original Hilbert space. Don't worry if you don't under dual space, let us skip for that, because that would again require a lot of explanation from Hilbert space, how we are linearly expanding. So this is one. So the bra and the ket. So let us return to the next space, things will become clear. So here it is. So you can see here that each ket vector belonging to a Hilbert space will have an existing associated bra vector. This one is the Hilbert space and this one is the dual space. Okay, now we come to the central part, very important. What is that? We all do matrix algebra, we all do score good in our university or our colleges, but what is the need? Why do we at all need matrix algebra? Is it that quantum mechanics is very inherent? Is it that it really requires matrix algebra? Let us find it out in this part of the video. So what I would like to tell you is a concept which is called qubit, or called quantum bit, and not only for quantum physics but for quantum computing also it is important. So qubit or quantum bit is like a basic unit of quantum information, and this is the quantum version of the classical binary bit that we call 0, 1, right? Physically realized with a two-state device, which is the bit 1. So a qubit is a two-state, we can say, or two-level of quantum mechanical system, one of the simplest quantum system displaying the peculiarity of quantum mechanics. Now, why it is peculiar, we will come to know. Let us take an example. Say, for example, the spin of an electron, right, which have two levels, can be taken up as spin up and spin down. But as we know that it is in a superposition, so it is both spin up and spin down. This is one example. I'm coming to the point why I'm telling those examples. We can also take something like this. This is called the polarization of light, of a single photon in which two states can be taken, either a vertical polarization as you see and a horizontal polarization, either of them. So what happens is that because we know all of them are in quantum superposition, so we have to take into account both of them. In classical system, generally a bit is something which has to be in one state or the other. So bit is something which has an OR condition. However, quantum mechanics allows the qubit, this one, it is basically a coherent superposition of both states simultaneously, a property which is fundamental to quantum mechanics and quantum computing. That means for a bit, classically it is either or, but for a qubit it has to be this and this. Remember that the coining of the term qubit is actually done by Benjamin Shoemaker, another American theoretical physicist. Now that we have understood what qubit is all about, and because qubit is something which is both of them, not something either or like classical bit, we will see something more. So if you see that in quantum mechanics, in general, the quantum system of a qubit can be represented as a linear superposition of two orthonormal bases or state vectors. And these are actually written, the quantum state is written as this, right? 0 as 1, 0 and 1 as 0, 1, right? Now these are written as we have seen by convention of Dirac's Bra and Ket notation. So what we can see is that these two orthonormal bases together comprises of what we say in Hilbert space. Now qubit states can also be combined to form product basis states. Okay? For example, if I show you two qubits could be represented in a four-dimensional linear vector space, then it would be this, it would be this, it would be this, and it would be this. So why I am showing all this, why I am talking about qubits, etc. Because here you see the matrices come. So the first reason why quantum mechanics will have matrix, or why we should learn linear algebra, is this one, that the basic root of quantum mechanics is on the qubit, which mentions a quantum state. And this quantum state is not just only 0 or only 1. It has to be both, right? Okay, I will show you further examples, will make things clear. Now, most of our work in quantum mechanics revolves around what is called a wave function, and it is written like this. And if you see that the complex conjugate of this one is a Bra vector, which we have seen, where this equals to this, right? So the product of Bra and Ket vector is basically an inner product scalar, whereas the product of a Ket and Bra vector is an outer product. Let us ignore this. I will come to that. Now, the use of Bra vector is quite wide in notation in quantum mechanics. So in the metric representation of this one can be represented as a column vector where the coefficients expand from C1, C2, so Ci, and it looks like this, right? So you see here again matrices are coming. So the Bra vector, which is this one, the Bra vector actually refers to a row vector of the conjugate expansion of Ci. That means it is a complex conjugate. And since wave functions are normalized, so what we get is that we try to write it in this way also, right? It gives us, because once we normalize, we get a value either 0 or 1. So this is another example, the second example, that because we deal with wave function and it can be represented as column vector, so we need to learn matrix algebra. Another very important, which dates back to the date of Heisenberg, is something which is called Heisenberg's matrix mechanics. Now, Heisenberg's matrices, it is the classical, I mean to say, when just quantum mechanics was evolving, consist of an array of numbers representing all possible quantum states of a particle or system's individual physical attributes, such as it can be energy, it can be position, it can be momentum, and before an event or interaction has taken place. That means it contains an array of physical possibilities where the subatomic particle would be. So here it is, all possible energy quantum states which attributes energy, position, momentum, and it looks something like this. So the rows M represents the initial quantum state and the columns N represents the final quantum state, and it can run up to infinity also. I mean to say the matrix can be infinite if M and N runs up to infinity. Now, the example opposite to is an infinite matrix containing all the frequencies, and it looks something like this, right? So considering the momentum P and displacement, say for example Q, of the above particles will also oscillate with similar frequencies, and that is why they can therefore also be represented as infinite matrices. So this one and this one shows the momentum as well as the displacement. So again we see that we come across matrix mechanics. So all these examples, starting from the basic qubit going up to wave mechanics and showing Heisenberg's matrix mechanics, actually spells out the basic idea of today's video, why you need to learn matrix algebra and how matrix algebra is intimately related to quantum mechanics. Okay, so because the video is going quite long, I mean to say I will just touch base onto matrices. So we can tell a matrix is basically a kind of a box, a representation of real or complex numbers. Matrices can be look something like this, right? All these are matrices. So given a many matrix Q, we denote the element Q sub ij is the matrix in the ith row of the jth column, right? And the jth column. So if a matrix has m rows and n columns, the convention is to say that it has a m and n matrix or an m and n dimensional matrix. For example, a square matrix, as the name suggests, is a matrix where the number of rows and columns are the same. And here I would like to show you, I have just shown that this M is an example of a square matrix, right? Okay, so this one part is clear that how a matrix looks like. Now let us see a quick example of this M, N dimension, etc. So we have seen this square matrix I have just told you. Okay, so let us take an example, the same one, this N1, and referring to the N and P, obviously we will take N and P only. So we have explicitly written down N12, so this means this one, 3, obviously the first referring to the second column, and this one would be P31 equals to -3, which would be referring to this. So obviously P23 is not defined as P has only 2 columns. So as you see, at first glance there doesn't seem to be much intuition about matrices, as we will see soon that a matrix can be thought of as a mathematical object acting on vectors, right? So you have to bear with me for the next video part, because we will look more into matrices. This part of the video is mostly given in order to make you understand the real need of matrix mechanics in quantum mechanics. Why do they need? What are the essential parts? And in the next part of the video, we are going to take up matrix addition, scalar multiplication, examples of matrix multiplication, and matrices as function on vectors. Matrices itself is quite a long subject which we will take on further. So that's it for today's video. I think that it is now becoming a kind of a motivation for you to learn more about matrix algebra, because now you have understood really the meaning and the need of matrix in quantum physics. Just subscribe to my channel Physics for Students, click on the bell notification and click on all to get all the notification from Physics for Students. So this is Shaunak signing off as of now from this video, but we will continue the mathematics of quantum mechanics until we get a solid understanding of everything. Thank you very much for watching this video. Stay safe and happy, and God be with you.
Thank you for watching this video. We appreciate your time and patience. If you want to connect with us and provide further feedback, comment or suggestions, please email us at contact.physicsforstudents@gmail.com. You can also follow us on Facebook, Instagram and LinkedIn. See you soon in the next video.